Ladies and gentlemen, welcome to the talk. I'm Lantao Yu, a final year PhD student at Rice University. I hope you can enjoy the video in the next 15 minutes. I'm Lantao Yu, the presenter of the paper titled Blind Multi-spectral Image Pan-sharpening. I performed the work while I was an intern at Mitsubishi Electric Research Laboratories last summer. Pan-sharpening is a task that aims to enhance the spatial resolution of multi-spectral imagery guided by the high spatial resolution panchromatic imagery. Since multispectral imagery and panchromatic image overlaps in electromagnetic spectrum, they are usually captured by two optical systems. Therefore, there often exists spatial misalignment between them. Blind pan-sharpening, therefore, addresses the problem of enhancing the spatial resolution of multispectral imagery so that it is well aligned to panchromatic imagery with consistent sharpness. There roughly exist two categories of approaches in the literature for blind pan-sharpening: model-based approaches and learning-based approaches. Previous model-based approaches are limited in a sense that the blur kernel estimation is often flawed and the cross-channel relationship is not well exploited. Learning-based approaches are limited for two reasons. First, for remote sensing imagery, it's difficult to gain enough training data, especially well-aligned data. Second, the trained model is not generalized enough to perform well across different sensor platforms. To address the blind pan-sharpening problem, we simultaneously perform image registration and pan-sharpening. Specifically, we use cross-channel prior for the panchromatic multispectral relationship and use total generalized variation for the blur kernel. So briefly, we formulate the inverse problem as the highlighted optimization problem. The first term is the data fidelity term. We believe X, which is the measured low-resolution multispectral image, comes from blurring and downsampling the target high-resolution multispectral image Z. The second term is the regularizer on the cross-channel relationship, and the third term is the regularizer on the blur kernel. Blur kernel not only carries the blur information, but also carries the misalignment information. The regularizer on the cross-channel relationship is very crucial. It determines what should the target multispectral image be. Since the data fidelity term has already had a very strict constraint on the low-frequency part of the multispectral image, naturally, the cross-channel image prior should regularize the high-frequency components of both imagery. Based on guided image filtering, if we have two well-aligned channels with similar sharpness, then a local region of one channel can be well approximated by a linear affine function of the other channel. This should also be true in the high-frequency components of both channels. By minimizing the overall squared residual, we write the loss function as highlighted. Notice that we are using Laplacian to compute the high-frequency components. That's why we call the prior as local Laplacian prior. For the regularizer on the blur kernel, let's think about the two-dimensional Gaussian filter, which are non-negative and smooth with sparse coefficients, and the coefficients are normalized to unit sum. Unfortunately, current L1-based regularizer on the gradient of the kernel coefficients often force small gradients to be zero. To address this problem, we use second-order generalized total variation on the filter coefficients. That is, we also enforce the second-order gradients of the filter coefficients to be small. This is reflected as the L21 norm of the epsilon of P, meaning that the ancillary variable P needs to be not only close to the gradients of U, but also needs to have a small gradient itself, which is the second order total variation of U. By reformulating the regularizer as augmented Lagrangian, we can solve it in the framework of ADMM. With the subprograms and the updated scheme like this, easily the XY subprograms can be solved using soft thresholding. The Z subprogram can be first reformulated by putting Z in the right-hand side of the matrix multiplication. Then it can be easily solved by conjugated gradients, followed by projection to the simplex. The UP subprogram can be solved by a fast algorithm using FFT. Due to the time limitation, I refer you to check out Lantao paper in the reference. The AC subprogram, which relates to the coefficients of the linear affine function, can be easily solved by guided image filtering. The capital Z sub I subproblem can be solved either by conjugated gradients or a recent fast algorithm proposed by researchers in University of Toulouse. Notice that the initialization of the Blur kernel is also very important because it can avoid being trapped by bad local minima. Here we assume that the stacked panchromatic image as a perfect target multi-spectral image in terms of position, and we use them to solve the initial Blur kernel. This is quite helpful, especially when the misalignment is very large. And before we get to the results, we would like to first see how good is each prior. For local Laplacian prior, we compare it with the local gradients constraints, which is LGC, which use gradients as opposed to Laplacian to extract the high frequency components in the task of guided image upsampling. We find our results are better than LGC, and the major reason is that from digital signal processing perspective, Laplacian more uniformly regularizes two-dimensional high-frequency components than the horizontal and vertical gradients in LGC. For the usefulness of the second-order generalized total variation in the Blur kernel estimation, we also conduct an experiment. We first have a ground truth Blur kernel characterized by Gaussian with some non-integer offset, and we use the Blur kernel to blur a panchromatic image, followed by downsampling and adding noise. The blurred, downsampled, and noisy image is called F. The process of generating F from the Blur kernel can be written as the Blur kernel multiply a measurement matrix E by solving the two optimization problems that regularize the widely used isotropic total variation and our used second-order generalized total variation. We can make a comparison in terms of the relative error. We easily find that under multiple noise levels, our relative error is significantly smaller than that from isotropic total variation. The images show when the noise level corresponds to 20 dB, second-order generalized total variation can generate a very close approximation to the ground truth Gaussian Blur kernel. The major drawback for the isotropic total variation, as shown in the left image, is that L1-based constraints will introduce sparsity on the gradients. This will force the small gradients to be zero, which violates the property of Gaussian low-pass filters or many other models of Blur kernel, because the gradients close to the center of the Blur kernel is small, but should not be zero. With the verified effectiveness of two separate priors in mind, we conduct our blind pan-sharpening experiment. We use Pavia University as the data. The data is basically a hyperspectral imagery. We use them to synthesize well-aligned multi-spectral image and panchromatic imagery. Then we generate low-resolution multispectral image by applying Gaussian blurring and downsampling as the input. By feeding them into our algorithm, we generate the output, which is the super resolved multispectral image that are supposedly well aligned with panchromatic image. We conduct two experiments. The first experiment corresponds to small misalignment, and the second experiment corresponds to large misalignment. We can conclude that in both experiments, we obtain consistent average PSNR, and the average PSNR is much larger than related work, with nearly 6 dB higher than High-Shor's PSNR. Notice that our approach is very robust to large misalignment, which not every related approach is good at. So for example, a recent approach published last year called BHMIFGLR is not quite good at this, which was trapped in local minima as shown in the left image. This is our zoom in comparison with BHMIFGLR with small misalignment. We can find that not only we reconstruct the details of the white line, but also we avoid the fake texture of the trees near the white line to the right, meaning that the ground truth has no textures, but the left image has textures which are fake. Compared with High-Shor, we have much higher sharpness of lines and more details from the roof of the building, the yellow building. We also compare our algorithm with a deep learning-based approach published by MERL in last year's ICASSP called Unrolled Projected Gradient Descent. We use the same AV iris data used with ground truth, high-resolution, well-aligned multispectral image, and the panchromatic image. We find that in the 4 test images, we have more than 1 dB higher mean average PSNR across 4 images. And if we compare the residuals in green channel of the Los Angeles dataset, we will find that our approach outperforms UPGD, and the improvement is mainly in the smooth areas. This is because that it is more difficult for a learning algorithm to be trained in a large variety of conditions, including blur size, misalignment level, noise level, etc. But it requires data, because it requires data to be provided for a wide variety of cases to provide robustness. In contrast, our approach adaptively determines a kernel for each test image set, providing more robustness, especially to the level of blurring under different blur conditions. So in conclusion, our paper proposed a novel blind pan-sharpening approach that uses local Laplacian prior to regularize the cross-channel relationship and use second-order generalized total variation to regularize the blur kernel. They both offer impressive performance, and when combined for blind pan-sharpening tasks, we generate the results with state-of-the-art performance in terms of visual quality and average PSNR. So the takeaway message is that, first, the cross-channel relationship should be focused on the high-frequency components of multispectral and panchromatic image. Second, previous L1 regularization on the blur kernel is limited because it will force small gradients to be zero, which deviates from the shape of Gaussian-like kernel. And we can use higher order generalized total variation to overcome the drawback. Well, thanks for listening. I can take questions now. Please feel free to ask.